When I was in high school, in my AP Calculus class, there was a poster of Euler on the wall. It looked a lot like this one shown here. This poster stared at me before I took every exam, every FRQ quiz, and every homework problem that I was struggling through at the time. It was a lot like Euler himself was silently judging me, reminding me of the sheer genius I was up against. At the time, I didn't know much about him, just that he had something to do with the strange number e, which popped up a lot in exponential functions and logarithms, as well as a method I needed to know for the AP exam. His name seemed to appear everywhere in math. During my freshman year of college, I attended an engineering seminar, where one professor with a heavy Arabic accent of computational fluid dynamics repeatedly screamed "Euler!" to a tired class, waking us up. Also note that he said if you divide by 0, you will go to hell. Back to Euler, as I learned more about him, I began to realize why this Swiss, blind mathematician was such a giant in this field. In this video, I will show you 2 important contributions made by him and why he can be considered the king of mathematics. When you see an f of x, summation notation of a sigma, e and pi, we can all thank Euler for standardizing this notation. He developed the calculus of variations, contributed significantly to the study of prime numbers, laying the foundation for modern methods in the field. Developed a numerical method for approximating difficult differential equations through Euler's method. Found the exact sum to the Basel problem, the infinite sum of inverse squares. Introduced the Euler fluid equations, which are important to the study of fluid dynamics. Here's a brief biography. Born on 15th April 1707 in the city of Basel, Switzerland, Euler would live a fulfilling life dedicated to the pursuit of mathematics, physics, and engineering, becoming one of the most prolific and influential mathematicians in history. Raised in a family that valued education, Euler's father, Paul Euler, was a pastor and initially wanted him to follow in his footsteps. However, the young Euler's exceptional skill and aptitude in mathematics became evident, leading to his father to seek the mentorship of Johann Bernoulli, whose family appears so many times in textbooks. Euler enrolled at the University of Basel at the remarkably young age of 14, and eventually earned his master's degree in philosophy there. During this time, he wouldn't only be working on mathematics, but in other subjects such as temperance and the history of law. In 1727, Euler moved to St. Petersburg, Russia to join the Academy of Sciences. Here he flourished despite challenges, including political instability and personal health issues. In his personal life, he had 13 children, of which 5 survived childhood, 3 sons and 2 daughters. It is said that Euler was known as a generous and kind person, devoted not only to his work, but also his family and community. Despite losing his eyesight later in his life, Euler's mental acuity and mental creativity remained undiminished. He continued to work prolifically, dictating his findings and solving problems through sheer mental calculation. Euler passed away on the 18th of September 1783 in St. Petersburg, Russia, leaving behind a monumental legacy. His work continues to influence modern science, engineering, and mathematics, cementing his reputation as one of history's greatest mathematicians. Here we will discuss 2 of my favorite contributions made by Euler. They are Part 1, Infinite Series, and Part 2, Complex Variables. We begin with Euler's study of infinite series. This was a hot topic for mathematicians in the 17th and early 18th centuries. But it wasn't until Euler came along in the mid-18th century and manipulated them in such a manner that we were able to solve many of its mysteries. For a calculus student, one of the first series we look at is the geometric series, which looks like this. Performing an index shift, we also get this. Its sum can be attained as follows. Start with its partial sum formula and split it as follows. Take note of the geometric ratio r, which must be between -1 and 1. With this in mind, we take the limit as n tends to infinity. We now break up the limit into 2 pieces. We recognize that the first limit term has no dependence on n, which means we can factor out an a over 1 minus r. Finally, the limit of r to the n, given r is between -1 and 1, this becomes 0. So this limit all simplifies down to a over 1 minus r, which we can finally show is the sum of the infinite geometric series. You can also see a visual proof, my favorite being this one from Proof About Words. You can see through similar triangles that this also provides a proof to the geometric series. But not all sums are geometric. Jakob Bernoulli had figured out the sum of these 2 before Euler came along. At this time, the infinite sum of the inverse squares has been a problem vexing mathematicians. Mathematicians have known that this series converges or approaches a number, but did not know its exact sum. One good try would be to bound this monster. This is what Jacob Bernoulli did. He first observed that 2n squared is greater than or equal to n times n plus 1. Rearranging this, we get this inequality. So making these into sums, we can rewrite this as the following. Jacob Bernoulli knew that the right-hand side converges to 2. Thus, the infinite sum of 1 over n squared has an upper bound of 2. And this can be similarly shown for p equals 3, 4, 5, and above. However, this problem remained a mystery, with Bernoulli stating, "If anyone finds and communicates to us that which thus far has eluded our efforts, great will be our gratitude." Enter Euler and his numerical approximation of the Basel problem. If we were to take its partial sum up to its 1, 10th, and 100th terms, we get a closer approximation to the problem. Clearly, numerical approximations won't give us the exact answer. So is there a better way of doing this besides brute forcing the problem? The answer is yes, and this is how 24-year-old Euler handled this approximation whose partial sum converges faster than just summing the inverse squares. Step 1. Improper integral and series trick. Euler began by defining I as this improper integral, expanding the numerator of the integrand as a series, and dividing each term by t. We then integrate term by term, and finally we plug in our bounds. In step 2, we are going to perform a substitution, so we let z equals 1 minus t. With the same improper integral as before, we perform the substitution. Note the first part, the 1 over 1 minus z, which can be expressed as this power series. We then distribute, which can be written as this sum of integrals. Make note of this integration by parts. This will come in handy in our next step when we perform the integration. When we integrate through applying integration by parts, we get this. Next up, we factor out a natural log z. In the first term, one can see that a series is that of negative natural log 1 minus z. Finally, plugging in our bounds, we get this. Euler wrote the ln1 times ln0 term. With our modern limit notation, it can be correctly interpreted as the limit of z as 1 approaches from the left of ln z times ln1 minus z, which is 0. So this term disappears. Okay, our final result step. Bring back what we had from before, we get this. The first term can be simplified down to negative natural log 2 squared. Equating the I from part 1 and above, we get the following. Lastly, the sum becomes as follows. Let's see why this is a better approximation of the 1 over n squared sum. So our original is 1 over n squared. Now our new sum has this 2 to the power of n minus 1 term, which makes it converge more rapidly. Let's see what happens when we make them into continuous functions and graph them. Let f be the original function, and let g be the one we just derived. Graphing the derivatives f prime and g prime, we see this. The orange g prime curve is steeper and overtakes the green f prime curve. That 2 to the n minus 1 makes a great difference in its convergence rate. Alright, so we use integrals, logarithms, series, and integration by parts to arrive at this. And this provides a faster way of performing this numerical approximation. However, this is still just an estimate. We need the exact sum. So here's how Euler did it, how he got the sum of 1 over n squared, otherwise known as the Basel problem. Begin with p of x as this alternating series. Note that p of 0 is equal to 1. We are going to cleverly multiply and divide this series by x. And multiplying it through the numerator, we get this. We now observe that the numerator is exactly the series expansion for sin x over x. Let's take a closer look at sin x over x. This is also known as a sinc function. Let's try to find the roots of this, which will be helpful later. So, p of x equals 0. This implies that sin x equals 0. Looking at the unit circle, this occurs in multiples of pi. This is true except for x equals 0, where p of 0 equals 1. Okay, so going back to p of x, this can be factored in the following form. Multiplying it through, it condenses down as this. Now we expand. So now we're going to compare ups to squared terms in the original p of x in the factorization. Homestretch here, so we have 1 minus x squared over 3 factorial is equal to what we just factored and derived that. Cancel out the 1's and x squareds and multiply both sides by -1. We get 1 over 3 factorial is the same as this sum. Factor out of 1 over pi squared, and the infinite sum of the inverse squares pops out. Rewriting this in summation notation, we get this. Moving the pi squared to the other side, we get pi squared over 3 factorial, and 3 factorial is 6. So the sum becomes pi squared over 6. So Euler had done something to stump the mathematical world for a long time, getting the exact sum for the Basel problem, which is pi squared over 6. Not only this, but Euler using the same technique was able to give values of infinite sums up to 1 over n to the power of 26, which is this chill guy. In the next century, Bernard Riemann would extend this to a whole nother level, the Riemann zeta function, and along it, $1 million problem, the Riemann hypothesis. However, one problem still stands. What about 1 over n cubed, or the odd numbers? Its exact solution is still unknown. This is now known as Apéry's constant. You can learn more about it on its Wikipedia page as shown here. It still remains a mystery, and I'm hoping a 21st century mathematician can find its exact sum. Next up, we are going to talk about imaginary numbers, or their preferred name, complex variables. The story of complex variables is an interesting one. It's filled with prejudice, abstraction, and finally, realization. One place where it shows up is when we are trying to find the roots of x squared plus 1. When mathematicians finally use I as an intermediate step for solving the roots of cubic polynomials, they began to realize something much more interesting is happening. With that in mind, we can finally solve nonsensical expressions such as e to the x equals -1 and cosine x equals 2. We define the imaginary unit as I squared equals -1, which to some may seem wrong. How can squaring a number make it positive? It makes no sense. We have numbers that represent counting things, negative version of those counting things, and numbers which are ratios of the counting or natural numbers. These make sense in daily life, whether representing monetary value, area, velocity, or others. The abstract concept of I finally came through when mathematicians left behind their notion of only having real numbers to having these abstract imaginary or complex numbers. At the core of understanding complex variables, it is Euler's formula. E to the ix is equal to cosine x plus I sine x. We also have the Morse formula, which is the following. We aren't going to prove it here, and I'll leave it as an exercise for you guys. A hint to the proof is to factor the Pythagorean identity. With those two formulas out of the way, we can finally answer the question, why are the Taylor series for cosine and sine x like the way they are? For a calculus student, you may argue it comes from Taylor's formula. Just keep differentiating until you see a pattern. But we're better than that, and we like Euler. Let's see how we can arrive at the series expansion for cosine x via complex numbers. We begin with the Morse formula, one for plus and one for minus. Adding the two together, the I sine n theta terms cancel out, leading to only a 2 cosine n theta. Now let's bring the 2 to the other side. We will apply and expand by the binomial theorem. Doing so gives us this great mess. When we combine the two, we see the terms nicely cancel out. Performing the substitution of letting x equals n theta, which is important as n tends to infinity, theta, which is x over n, tends to 0. We should also remember these two trig limits. Also, as n tends to infinity, the n-1, n-2, n-3, and so on can all be replaced by n. Doing so gives us the following. And when we simplify it down by cancelling out the n's, we arrive at this series, which in summation notation is that of precisely of cosine x. So that's how we get cosine x's Taylor series. I will leave it as an exercise for you to find the series representation of sine x. We are now going to do the derivation of Euler's formula in a bit of an unorthodox manner. One could derive it with the Morse formula, but I like this one a lot more. First, we let y equals sine x. This implies that x equals arc sine y, which can be interpreted as this integral. Next, we let y equals iz. giving us that dy equals I dz. So looking at the integral and applying the substitution, we arrive at the following. Bring the constant I to the outside of the integral, and simplify what's in the radical. Now we can easily integrate this through a trig substitution, giving us this antiderivative. For sake of simplicity, we're going to do something a bit taboo and ignore the plus c. This is because of how x is defined. Next, as z is equal to y over I equals sine x over I, we can square both sides and say that z squared is the same thing as negative sine squared x. Substituting these values into x, we get the following. The term under the radical can be simplified down by the Pythagorean identity, and for the second term, 1 over I is equal to negative I. Next up, we multiply the left-hand side and right-hand side by I. And since I squared is equal to negative 1, it becomes negative natural log. By the log power rule, we can put this inside of ln, and simplifying it further through the log quotient rule, we exponentiate both sides, and ta-da, we get Euler's formula. So this is the Euler's formula, and something really cool happens when we plug in pi. Remembering our unit circle, we see that e to the I pi equals negative 1 plus I times 0. The imaginary part on the right hand side goes away, and moving negative 1 to the other side, we get e to the I pi plus 1 equals 0. This is considered as the most beautiful equation in math, uniting our friends, e, the base of the natural logarithm, pi, the circle constant, and our imaginary friend I, alongside 1, which is the multiplicative identity, all equaling to 0, which is the additive identity. I end this section on complex variables with some exercises for you. First, show Euler's formula by Taylor series. Next up, find I to the I. Finally, Bernoulli believed that ln negative x is equal to ln x. I want you to disprove this. Also, find a factor these two logarithms differ by. Your final answer should be in its simplest form and not as a logarithm. This video is based on 2 chapters in Euler, the Master of Us All, by William Dunham. We only covered 2 topics, but the book goes over a lot more, including number theory, logarithms, analytic number theory, algebra, geometry, and combinatorics. And with that, thank you guys very much for watching, and I'll see you in the next video. Bye.